What's up guys, it's me, Sir Ernest, and today we're going to talk about rectilinear motion. When we say rectilinear motion, we say that the motion is on a single straight line. And in this case, we're going to discuss uniform acceleration. Okay, and when you say uniform acceleration, that means the direction of the acceleration is in one direction and the magnitude of the acceleration is constant, and this is done by applying a constant force, and that's by virtue of Newton's second law of motion. Again, here we're going to assume first that the motion or the particle that undergoes this motion has a constant mass. So say we choose this particle to be moving along a single direction. So let's say along the x-axis. So if this, for example, this is your origin and this is your particle. So here we set that the particle's position is given by this position vector x. Okay, and let's say that the particle is moving with the velocity v. So here the position x in terms of unit vector notation is x I hat, where x is the distance of the particle of mass m from the origin. On the other hand, the velocity of your particle is x dot I hat. Okay, so the equation of motion in terms of Newton's second law of motion in one direction or in one dimension is now written as F, which is along x, and usually if this is a general form, we don't consider first a constant force, but instead this force may be a function of position, velocity, or time, and this is equal to mass times the acceleration along x. Here F sub x is the force along the x-axis. As I mentioned earlier, it is a function of position, velocity, and time. Now, as I mentioned before, if we're going to consider a force that is a constant, so that means Newton's second law becomes Fx equals mx double dot. So here we already removed the unit vectors because everything is happening in one direction. Okay, so now this becomes m times the derivative of x dot with respect to time, and this is a constant. So from here we can define the acceleration x double dot, which is the derivative of x dot with respect to time, and this becomes f x over m, and let's call this a, and this is a constant because fx is a constant and m is a constant. So f over m, which is a, is also a constant. Now the important point is that this is an example of a equation of motion. And from here, we can determine other physical quantities such as velocity and position. So for example, if you want to we want to know the velocity of your particle, so what we can do is we just integrate or solve this differential equation by direct integration with respect to time. So how we're going to do this? So we multiply both sides of the equation by dt. So this becomes integral of dx, and this is equal to the integral of a dt. So usually when we do this, we do a definite integral wherein we start at an initial time, let's say time equal to 0, and then at time equal to 0, sorry, this should be x dot, sorry about that. X dot at time equal to 0, let's say, is x naught. So this tells you the initial position or initial velocity of your particle. And then at later time t, the velocity of your particle is x dot. Okay, so from here we can now solve this as follows. This becomes x dot minus x dot naught, so this is x dot naught. This is equal to a t, or more conveniently, the velocity as a function of time is equal to the initial velocity plus the product of the acceleration times time. So let's call this equation number 1. Now, similarly, we can calculate the position function of your particle by again integrating this directly with respect to time. Okay, so here when you integrate this, this becomes x as a function of time. This is equal to x naught plus x naught dot t plus 1/2 at squared. So here we define that the position at time equal to 0 is x naught. You can do the integration later. Okay, and let's call this equation 2. As you will notice that these two equations are already familiar to you. Now, let's say you want to eliminate, we want to combine equation 1 and equation 2 through elimination of t, or time. So for example, what we can do is we can rewrite equation 1 as this. So t will now be equal to x dot minus x dot naught divided by a. And then we substitute this here like this. So this becomes x equals x naught plus x dot naught times x dot minus x dot naught divided by a plus 1/2 a times x dot minus x dot naught over a squared. Now if you're going to expand this and then simplify, we end up with this expression: x equals x naught minus x dot naught squared over 2a plus x dot squared over 2a. And simplifying this, we can rewrite this as 2a. So transpose x naught to the other side and then multiply both sides of the equation by 2a. So this becomes 2a times x minus x naught equals x dot squared minus x dot naught squared. And this is, let's call this your equation number 3. So equation number 1, as you will notice, together with the equation 2 and equation 3, are the familiar kinematic equations which has been introduced to you in your high school and your university physics classes. Okay? And these three equations stem from the fact that the particle is undergoing is moving in a single straight line, and it's undergoing uniform acceleration caused by a constant force. Okay? So that's it. That's your rectilinear motion. In the following videos, we're going to try to implement these kinds of solution to objects undergoing constant motion. Okay? So for now, thank you guys for watching. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.